Okay, so here we have an unknown, and you're going to tell me which forms, which functional groups, and what forms that molecule would likely give me that spectra. So again, what are we looking for first? Where are we looking, on the upstream or downstream?
Can you say smaller number?
Upstream is the larger number.
Downstream.
Yeah, higher frequency. Okay. So you always look, when you're looking first at something you don't know, you always look upstream. Okay? Because if you look downstream, see how complicated that is? That's hard to read, isn't it? Okay. So you always want to go 1440, 1400-ish and above. Specifically, I would actually start in this region right here. Okay? All right, now, so what sort of groups do we have? Do we have alcohols, amines? No, we don't have alcohols and amines. What do these tell us right here? That's at 3,000 to 2,900. They're strong bands. Carbon, hydrogen, right? So these are carbon, hydrogen, single bonds, and an alkane. That's what all this stuff is right here. We have one that's a little higher frequency right there. Okay. Notice that would be up closer to 3,100-ish, right? What sort of stretch would you see? What sort of band would you see at 3,100-ish? Still carbon hydrogen, but what is it attached to? What is it off? An alkene, yeah. Yeah, it's some sort of double bond here that's attached to, right? And so it's causing it to shift upstream. All right, so this one right here tells us that we either have some form of aromaticity or we have some form of double bond. Okay, there's something very easy you can do to double check that information of whether you have some sort of double bond or not, right? How would you do that? Perhaps using this information right there. In number of hydrogens. See how far we are from saturated, right? Yeah. So we need to get our IHD. What's our IHD for this? Yeah. Okay. So yeah, we would go the 2 times the number of carbons plus 2. Subtract off that. So we have 2 times 8, 16, plus 2 would be 18, right? We subtract 14 from that, that goes 4. Divide by 2 because that's the number of double bonds or cyclic elements we need, right? So, okay, so that told us we need 2 double bonds of some sort, don't we? Right? We found one of them, haven't we? At least to some degree. We found out that we have hydrogens that are attached to a double bond, right? A carbon-carbon double bond, some sort. And so that actually gives us a lot of information, a lot of hint, right? Okay, so what else can we look for? Are there any other places on here that we could look, perhaps, to see what type of double bond we have? Or if we have a ring, or what's going on here? Okay, so if we have a carbon-carbon double bond, that would be a what? Alkene functional group, right? Is there a place you can look for an infrared band that would be associated with the stretch of an alkene functional group? So we'd go to our table, we'd look at alkene functional groups. What's the wave number range on our table? Okay. What exactly are you looking at right now?
For the CH stretch connected to an alkene.
Yeah, that's the CH stretch. That's up here. So the CC stretch for an alkene.
Is it between 1620 to 1680?
Okay. So 1620 to 1680, right? Do we have something that's near that range? We have 1682, don't we? Yeah. And so that's probably our alkene stretch, isn't it? Oh, wait. What are you looking at?
Looking at the absorption frequency.
Okay. For where are you guys? Okay. And I look here. What are you exactly you're looking at?
The alkene, C alkene is between
Oh, okay. Okay. 1620. Yes. Okay. I didn't hear your lower range. Okay. All right. Okay, so do we have anything that's near that range? We have two bands that are near those ranges, right? Okay. So we have the 1617, right? That's just below the 1620. And then we have the 1682, which would be just above, right? Anybody remember anything about like conjugation and that sort of thing? Mm-hmm. Yeah, lowers frequency by like 20 to 40, right? Exactly. Perfect. And so if we have two double bonds, one of the things that they could be is conjugated, right? Okay, and so this would be expected to be the lower one then. Okay, so is there another double bond that would be a higher frequency? It's not alkene, right? Is there another type of double bond you can make? Perhaps that includes an oxygen. Carbonyl, right? Okay, so you can make a carbonyl. This makes a lot of sense because you did not see an alcohol, did you? If you have an oxygen, you only kind of have three options, right? You have carbonyl, you have where it's an ether, you have where it's an alcohol, right? And so those are the only real three options that we could have had here. We don't have the alcohol. We have something that makes a lot of sense to be a carbonyl. What's the range for carbonyl again?
types of carbonyls.
Okay, so it would not be, do we have any other oxygen? You only have one oxygen, right? So the types of carbonyls are what? Go ahead and look, everybody. Ketone and aldehyde, right? Okay, and what are the other types?
Amide, ester, and carboxylic.
Yeah, amide, ester, carboxylic acid. Can we have any of those other ones? No oxygen, no nitrogen to add to those, right? So it has to be a ketone or aldehyde, doesn't it? Okay, so what is the range for the ketones and aldehydes?
1680 to 1750.
1680 to 1750. Yep. Okay. You're starting at the lower number. Okay.
Yeah.
Okay. 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 By the way, whenever you tell somebody these ranges, because we organize these upstream to downstream,
Oh, okay.
you typically tell them upstream to downstream. That's like the, writing a sentence left to right versus right to left. Yeah. So that's what I'm saying earlier. Read the sentence backwards. Okay. And so this is actually a little on the low side for this, wouldn't it be? Okay. So again, that would be evidence that, hey, maybe this is conjugated, right? If these were conjugated together, then that makes sense that they're both a little on the low side. All right. So we now have evidence that we have a carbonyl. It is conjugated to our alkene. We know that the alkene has to have hydrogens on it, so it can't be super branched, right? It can't be completely branched. We also have alkane hydrogens. Okay. Anybody have any proposed structures they want to propose now? Can anybody draw out a structure for this that would fulfill these conditions so far? There's a few of them. Okay, so how many carbons does it have? Okay. We're going to draw a structure up here. You guys have to come up with it. No matter what, we're starting the next chapter next time. So if you don't come up with anything and you resist me the whole way, then you guys are just going to have to study the rest of the material on your own. Okay? So, what could be a possible structure? How many carbons? 8. Okay. So, probably the easiest thing to start with would be what? A straight chain, right? Okay. You could branch it. That's fine. There's nothing so far that we've seen that says there could be a branch. That's actually where you need to go and very carefully go through these right here and say, how many bends do I have that are different? Okay? Okay. And so I start with a straight branch. 1, 2, 3, 4, 5, 6, 7, 8. Do I have 8 there? Fantastic. Okay, and so there's several different places I can go ahead and put this conjugated system, right? Okay. So where could I put this conjugated system? Mm-hmm. Yeah, I could put it in the middle. I can also put it, do we have any evidence for a carbonyl hydrogen, though? Did anybody see a CH stretch that's on a carbonyl? We didn't, did we? Okay, we got to conjugate this group right here, the alkene, but we need to make sure that we don't end up having any hydrogens for the carbonyl, don't we? Okay. Okay, so one of the possible methods we could do here is we also only see how many bands right there. No, this higher frequency one. Yeah, so you'll see here, like, we have a whole series of bands, right? See that? Ding, ding, ding. Okay. This right here, though, we only have the one band, don't we? Okay. So what does that tell you about that hydrogen? Is there several different hydrogens? Yeah, we need one that ends up being directly on it, right? Okay. So we need very symmetric hydrogens there that aren't going to show up a bunch of places. Okay? Okay, so one of the ways we can do this is we can go ahead and put the double bond at the end, and then we can conjugate it like that. That would be an option. Some other options would be things like this. Okay, folks. And notice that we're adding extra branching. This gives us more hydrogens here. And that's actually why we are adding extra branching. Okay? That one's not super obvious. It gives us more states the hydrogens are in, right? More different hydrogens. Okay? Which gives us the extra hydrogens right there. Mm-hmm.
So if it was a straight chain, like the one we drew out,
Mm-hmm.
that peak for the alkene would sort of just be like, it'd be more narrow, there wouldn't be as many.
Yeah, so this gives us only, we have the CH3 here, we have the CH2s, and then this one might be a little different. And then this right here would give us our hydrogens off of that double bond. Yeah. If we have a lot of branching, this would give us more peaks here. It would also give us more peaks right here. And so we'd have a very complex series of peaks here. I'm going like this, but they'd all be grouped up here. Okay, and so you should expect to see more stuff coming out of here. Right. The important part here, though, is to get the conjugated system, to get that has limited numbers of hydrogens coming off, not a hydrogen off that carbonyl, and to get that you have not a lot of other functional groups, right? I.e., no other functional groups. You got a conjugated carbonyl, alkene, there you go. those would be the really important parts to get that you would be able to do this. Okay, let's draw another possible structure that's consistent with our spectrum that we did before. Okay, so draw one more structure other than the ones I just did. By the way, Blaze, you weren't wrong. I just was avoiding something, right? Okay.
I'm sorry, I'm still a little confused. So all those structures on the other page, those are all acceptable solutions?
They are acceptable solutions, but I don't want you to use them. There's also other solutions that would work.
Okay.
Like, we haven't done every single branching and place you could have put this, and like, these are a fair number of them.
Okay.
But I've purposefully left one. So we actually have all the elements at this point. All you need to do is just rearrange it slightly. So it's not one of those things. And it still fulfills the conditions we were talking about before. Okay? So what were the conditions again? Conjugated, right? No carbonyl hydrogen. We have CHs that are alkanes, so you can't get rid of all of them. Okay? And we have CHs that are alkenes as well. See, you can't get rid of all those, right? Okay. Those are the really important conditions, okay? Note that I did very purposefully avoid several questions during that thing because you guys were hitting on answers, okay? So there's a reason I just outright didn't answer some of the questions, okay? Folks. So, everybody got an attempt at rearrangement? We're going to go ahead and go on. Okay, so again, one of the most important parts is that we have this conjugated system, right? As long as you have the conjugated system, there's actually not a lot of ways you can mess this up, okay? So you kind of want to start with your conjugated system of the alkene and the carbonyl, right? And then we know we need one more carbon attached to that carbonyl. So we block the sites off for the hydrogen. Okay? So that's the central part that you should go ahead and draw it, okay? So as you may have noticed, Blaze, this was the one you were trying to do. So you had been mentioning putting it in the middle, and I kind of like sidestepped you and just went, let's put this at the end. And that's why, is because you're answering my question. I didn't want it answered yet. Sorry. So this obviously is an option as well. We could have placed this over here. Notice it still has hydrogens right there and there. And so we would still get our alkene CH stretches, wouldn't we? Okay. Note that if you put it on the other side, that's just the same symmetry, isn't it? Everybody say okay? Okay. So that's just that flipped. Over here, notice we just rearrange some of the branching a bit. It's fine. We still have that same complexity of CH stretches. right now, up to this point, without doing a full spectroscopic analysis where we assign every single peak, we probably couldn't differentiate between these. Mm-hmm.
Is there a reason why P doesn't have 8 carbons? Or am I just seeing it?
2, 3, 4, 5, 6. Oh, maybe. Yeah. 1, 2, 4, 5, 6, 7. Whoopsie. Yeah, I just forgot one, I guess.
Okay.
We add it to that side, or does it matter?
It doesn't matter. Yeah, it doesn't matter at all. This side would make it symmetric, I believe. No, it wouldn't. Ooh, so there's actually another option that I just didn't write. Yeah, but you can add it to either side. It won't matter. Which gives you your other options, by the way. Yeah. Does this one have 8? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. Okay. Okay, try this one. Give me the answer for that. Again, when you're first starting with these, following the step-by-step procedure is not a terrible way to start. So you want to go ahead and follow the step-by-step procedure and go ahead and have a table. I'd recommend you actually print them off while you're working on these things. Plus, guess what you're probably going to need during the test.
Table.
Yeah, it's open notes, so I don't really provide a lot of that stuff, right? Because I expect you to show up. But, yeah. Once you move beyond this course, that's when you can drop the step-by-step procedure, because you'll already do most of the things just by glancing at it. Okay, folks. You okay? You okay?
Yeah.
If you want some tea, you can flip my water on and give me. Tell you what, a lot of people are getting sick lately, aren't they? God, I must have had 20 doctor's notes this week. Yeah, making our way into my email. Okay, folks. So you should have made some decent progress right now. Again, we start where again?
Upstream.
Yep, upstream. Very good. Good usage of the language. Okay, and what are we specifically looking at in this case? So what sort of hydrogens do we have? Alkanes, yeah. So we have CHs that are just the normal CHs off of an alkane, right? And that's that 2800 typically to 3000, right? Okay. Okay, so we also have a band right there, don't we? About what that is that? Yeah, so there's a couple options, isn't there? There's nitrile, makes a lot of sense. The carbon-nitrogen triple bond, right? There's also carbon-carbon triple bond that could have fallen in that region. Okay. So we got to differentiate between those two. We can go ahead and build up some more evidence that we could have a triple bond here. How can we build up some more evidence? Saturation. IHD, right? So are we saturated? No. How far are we? Yeah, so we got a nitrogen here, so you have to use the nitrogen rules, but yeah, we're 2 IHD. You got it? And so 2 IHD would tell us that, yeah, triple bond makes sense, doesn't it? That would give us 2 IHD, wouldn't it? Yeah. So evidence is mounting. We have some sort of triple bond. All right. What would we expect if we were to have a...
So the IHD is plus the number of nitrogens?
Yeah, so we would normally go 7 times 2, right? 14 plus 2, 16. We get a 3 then, right? And then we would give another one for the nitrogen, because if you add a nitrogen, you can have one more hydrogen on there, right? No, like an oxygen, normally if you put an oxygen in place of a hydrogen, it normally has one other hydrogen on the other side, right? Nitrogen can have 2. Yeah. So that's kind of the way I remember that, is that nitrogen actually adds an extra spot. Okay. Yeah. And so that gives you 2 IHD. Again, we have a lot of evidence we have a triple bond, don't we? Okay, we got peak. The only real thing that could have explained that is a triple bond of some sort. We have IHD that says 2. That would be a triple bond. Okay, so nitrile would that have any hydrogens on that triple bond? No, there wouldn't be any hydrogens on the triple bond, right? A terminal alkyne, would have a hydrogen, wouldn't it? And then a middle of the chain alkyne would not have hydrogen, right? So do we have a hydrogen that would be attached to an alkyne? Okay, so we'd go CH stretches, right? What's the frequency range for a CH stretch attached to a terminal alkyne? Yeah, very high, right? Yeah, we don't have anything strong there, do we? So that can't be. So we don't have the terminal alkyne. The terminal alkyne is the only alkyne that's actually a strong, relatively strong band. Okay, it's usually in the medium range. What would a non-terminal alkyne look like? Almost no intensity at all, right? So we'd only see a very little peak if we see anything. Okay? And so this is probably not an alkyne, is it? And so you were exactly right. Nitrile. Nitrile. But we need to prove it, right? We need to build up evidence around it. Because what do scientists never do? No, they do the exact opposite, right? We never prove anything, but we build cases for things, and we never make authoritarian statements, right? It's not, it is this. It is. The evidence supports it being this. By the way, in your lab reports, do you say it is this? Ever?
No.
Period? No. What do you always say? The evidence supports, yeah, or suggests this. Okay. Okay, so you have some sort of C triple bond. It's in this ring. We also have an oxygen here. Do we have any evidence for a carbonyl? No, we don't, do we? Do we have any evidence for a OH, an alcohol? No again, right? So what's the only type of oxygen that doesn't have those two things? Nope, that's carbonyl, right?
No, then never mind then.
Yeah. So it can't be a CO double bonded. It can't be a OH. So the only way to not have those two things is to have a carbon on one side, an oxygen in your chain, and then a carbon on the other side, right? You have to have that, i.e. an ether. Yeah. Or an ester would also have been that oxygen, but we don't have another carbonyl, right? So, okay. So go ahead and make your attempts to draw. And the proper, some of the possible outcomes would look like this right here. So something like that. You have a nitro, you have a carbon chain, it needs to be an oxygen in the chain somewhere.
Why cannot be aromatic since the frequency?
No aromatic, well, first off, you don't have the IHD to be aromatic.
Oh.
You've already consumed your entire IHD budget. And so you just have no more double bonds put in.
Oh.
The other part of it is it does not have a CH aromatic. It also doesn't have the aromatic carbon set. Does that make sense?
Yeah, that makes sense.
Okay. So like, yeah. Yeah. That one, I did it with like just looking at the Spectrix. I didn't see the stuff here. But yes, you're right. That would be part of the checklist to do. And you'd look here. Again, I kind of did that because I said there was no hydrogens on any of these elements, right? Yeah. And we also don't have the aromatic set.
Can you explain again how you got the IHG? Like you did your 2 times 7 for the carbons, and then you did what?
So
past that?
2 times 7 plus 2, that's the normal IHD, right? Oxygens don't affect that because oxygens would just have another hydrogen on the other side, or they'd take 2 and it'd be somewhere else, right? And so the nitrogens, though, always affect your IHD number. And that's because nitrogens have 2 other bonds to them, right? So they're not just an extension, they're an addition on. And so we would go 2 times 7 plus 2, that'd be 16. That gives you a 3 so far, hydrogens that we're short. And then we'd have 1 more hydrogen we'd be short because of the nitrogen.
Okay.
Because nitrogen gives you an extra spot. And so that would then be 4 divided by 2, which is your IHD number. That makes sense?
So you got 14 and plus 2, which was 16, and then you divided,
And then I added 1
and then you added 1,
because of the nitrogen.
so it was 17.
And then I subtracted this off,
Okay.
and that gave us 4. So 17 minus 13, 4,
Okay.
and then divide by 2.
Alright, thank you.
No problem.
I have a question.
Mm-hmm.
So how does 2 IHD tell you that it's a triple bond? I thought that meant
It doesn't. What it does do is it gives you evidence. Okay? So, for example, this tells us we have a triple bond almost certainly, right? Of some sort. Okay? There's very few other things that could show up in that region that would not be a triple bond. And nothing anywhere near that strength. So, that gives us a piece of evidence that we have a triple bond. And then our IHD gives us supporting evidence, which strengthens the case, right?
And how does it give supporting evidence?
Because that means we have 2 pi systems. So we have to either have 2 double bonds, which we don't have any double bonds, or we have to have 2 ring systems or some combination there, right? Or a triple bond. Okay. So the ring systems technically would have been possible, but we also had this evidence right here, right? And so with those 2 pieces of evidence together, we have a very strong case for having a triple bond. Okay. Is that making sense? Yeah. Okay. Any other questions at all? No? Okay, fantastic. Now, yes, again, there are multiple structures. It could have been, this is just a selection of the structures that are kind of representative of what you could get. Okay? Mm-hmm.
Never mind. I think I was looking at the wrong thing. Yeah. So you can't, there's not like a carbon oxygen band that shows up. Because the one on the chart is alcohol, ester, ether, carbon single bond to an oxygen
Mm-hmm.
at 1,050 and then 11, or 1,150. So,
Yeah, that'd be way down here.
okay. Is
But-
that like,
We, so yeah, this is probably the carbon oxygen ether band stretch.
okay.
But we don't really need that because we already have all the evidence we need up here, and so we don't have to go to the lower spot. Yeah. But yeah, if you wanted to try to differentiate between these, and we wanted to go further, we could actually start differentiating between these. I don't know if we'd actually be able to get all the way because I haven't actually went through and done a full spectra of this and actually assigned all the bands. But we could definitely differentiate between the symmetries, and we can definitely differentiate between if these had branching near it. Okay. So we could do some more work. We're just going to stop here because that's not one chapter of learning. There's an instrumental course. My chemistry people will be doing an instrumental course. We'll go further into it. If anybody wants to do it, go further into it. Instrumental. It's good stuff. You learn how the actual instruments work. Okay, and so again, these are going to be a little bit deeper of a look for the infrared bending vibrations. These are the stuff that's in that fingerprint region typically. You notice these all start showing up in the fingerprint region. And this is how you can further differentiate, right? I'm only going to really kind of touch on this. I'm not going to go too far into it because for the most of you, you will never actually assign these. You might look at some of the strongest bands that show up and go, is it consistent? And that'll be about it, okay? For most of you, you're going to use functional groups, and it'll actually be scanning through samples to look for those functional groups. And that's how things like infrared microscopy work, okay? Or Raman microscopy also works like that, right? And so the vast majority of you will use something like that. You may not realize it yet, but many of the instruments you can use at a hospital to scan like surface of skin and that sort of thing, or biopsy samples, those all actually use infrared usually, okay? Anyways. So this right here is your types of bonds, and this right here is the number of bands that you'd see for those bonds, and this has to do with the different types of bending that can happen with that. Okay. This is your frequency region again. Notice this, for example, has two bands that would show up, and so you have two band spots, right? That you'd expect to see them. This is the appearance. So, for example, a terminal alkene has a pretty strong absorption, right? Kind of like the terminal alkyne, okay? It just absorbs lower down. All right. Anybody have any questions about that table so far? Okay. Notice that, by the way, aromatics, ortho, meta, and para, you can actually somewhat differentiate these aromatics from each other by using where these bends here, you have a strong band in this region right here. Okay? So for example, your spectra that you need to look at for the formal lab report, you can actually tell whether that's ortho, meta, or para based on where that peak is. Okay? And that's actually one of the only ways you can tell that. You can't do a GCMS. It's very hard to do with a lot of the other methods. Infrared is one of the methods that can do that. Okay? It's actually one of the most useful things about it. So you can actually differentiate fairly small differences in functional groups. Okay? All right. By the way, cis and trans, you can also differentiate using infrared. Okay? So oftentimes, conformations are the ones that you differentiate using infrared. Yeah. And people that skip infrared usually get the wrong isomers for what they patent. Yeah. So this right here is another example. So let's look at the substitution patterns from our bending vibrations. Here we have the aromatic ring again. This one is mono substituted. And so you actually see the set of bands right here. Okay. This here is di substituted. That's the para substitution in this case right here. And if we look up here at the table again, we can look at para substitution 8 to 830, and this is 830 right here. Everybody see that okay? And so this gives you a way of differentiating again your substitutions on your benzene rings. Okay. Okay. So let's go ahead and talk about the ultraviolet visible spectroscopy, because that's also going to be part of this chapter, because it's an absorption spectroscopy. By the way, is this a destructive or methodology, or does it conserve your samples? Do you have to destroy your samples to use spectroscopy like this? So infrared, Raman, UV, Vis, these are all non-destructive methodologies. Okay, you can actually take like a painting and just do a full infrared spectra of it, and you need proper equipment, but it won't damage it at all, other than being exposed to light. You're actually doing a form of spectroscopy to each other right now. Okay? It's visible light spectroscopy when you see something, isn't it? Yeah. In fact, that's how Raman did his. All right. So, GCMS, is that destructive or non-destructive? Destructive. Yeah, I actually have to take my sample, inject it in, and then I literally fraction it, right? I literally pass it in a beam of electrons, or it's going to destroy it. Okay? And so if you take a painting and do the GCMS, you actually take the corner of the painting that's hidden by the frame, and you take a little solvent and take up a sample and put that in the GCMS. And if you do that enough times, you'll have little dots all over it. Eventually, it would destroy the sample completely. Now, they've gotten pretty good at taking very small samples, but that just means you can do a few more times. All right, now, this right here is going to be visible ultraviolet spectroscopy. I believe, is anybody doing the biochemistry stuff and has used the visible light spectroscopy over there? Is it also a UV? Mm-hmm. I'll look at it. I don't know. I haven't looked. I haven't got a chance to see it. Yeah. I'm not entirely sure what's hidden. So oftentimes the same instrument can do both, because in reality visible light is not actually its own thing. Okay? Visible light is actually a subset of ultraviolet, really, for the most part. Okay? And so most instruments can do the both parts, but many of them do not, to save cost, because the bulb. They can buy bulbs that, just are used for people that don't give off UV, right? Like, you wouldn't want the LED to give off UV right now, right? That'd be a bad idea.
Get a nice tan.
Yeah, you would. I probably need the light bulb to give off UV. So your source here is just going to essentially be a light bulb. Most of these instruments, it's literally an LED like you'd buy on a projector or something, or a light bulb. And then you shine the light, you put it through an entrance slit. This is going to just be a very thin slit in a material. And this is literally just making it so you only have a very narrow beam coming through. Okay? And what this does is it keeps things from scattering off and causing you to have a bunch of blurred images. You guys ever seen like a flashlight, how it has rings? That's because that doesn't do a slit. Okay? You lose a lot of the intensity, but it narrows it and focuses your beam. Okay, this is then going to go through what's called a dispersion device. Anybody know what a dispersion device is normally called when you guys look at it?
Prism.
Yeah, it's a prism. In this case, they put a prism. You don't necessarily have to do a prism. It actually can be grating as well. So like really thin lines cut into something. Or there's a few other selection devices. But what this is doing is it separates out the different frequencies of light. Okay? And then what you're going to do is you're going to take those separated out parts of the light. So it has all the different colors. In this case, if we're doing UV as well, it would also be ultraviolet, which don't have color names because most people can't see them. And then you're going to do an exit slit. Basically, it's going to block all the other colors except for the one you're selecting at that time. Okay? All right, so this is actually, if anybody's used a visible light instrument, did you guys use that in general chemistry?
I don't know.
It probably would have been the vernier. You would have a little black box that you attach to those lab quests, little cuvette. Okay, so that was a visible light system. You saw there's a little light bulb in there. You would have selected for the frequencies that you wanted to do. It would have actually selected that frequency using this right here, this little slit. And then you would have actually passed that through your sample. You'd measure the initial source intensity and then the detected intensity after it passes through the sample. That would give you percent transmittance. Okay? So that would be the source dividing the detected light. You did that by taking a background and then running a sample, right? Okay. Then what you would do is typically you see these in absorbances. To get absorbance, you take the negative log of the decimal point version of percent transmittance. Okay? So the negative log of the intensity of the sample divided by the intensity of the background, or the negative log percent transmittance divided by 100 to get not in a percentage, right? Okay. And this right here would be an absorbance versus wavelength spectra. This is normally done in absorbance because oftentimes you want to use Beer's law with this. Does anybody remember Beer's law at all? Okay. Okay, that is absorbance equals path length times the concentration times epsilon, which is the absorptivity. Okay? So it's the absorbance, which we just looked at how to get, and then it would be equal to how long of a path this cuvette is. By tradition, this is 1 centimeter, because this value right here is in centimeters. And so all cuvettes are 1 centimeter, and then you put path length 1 here. And anything multiplied by 1 is same thing, right? Okay, and then that would give you concentration right there. Concentration as the concentration of your solution, right? Okay. And then absorptivity is typically found experimentally. You then use that value for a number of different cases. And notice that you can actually solve so that you can put, these are constants then. And you have a linear relationship between absorbance and concentration, don't you? And so this is what typically people use UV vis for, is they use it to monitor concentration of a thing that they know where the peak is. Okay? Used a lot in biology, like protein purifications, how much protein is in something, how much substrate is in something, do you have the proper levels of X, Y, Z? Almost all of these are done through UV vis, Beer's law. Okay? Factories do it all the time. Like Coca-Cola literally has a little Raman instrument that triggers something 1,000 times per minute at the end of their line, and is running this calculation constantly to make sure it has the correct concentration of specific ingredients. So, All right. So right here, again, we have a wavelength max. This is, everybody see that? That's the symbol for wavelength, right? Subscript max. It's literally just the wavelength that you have your maximum absorption for. And in this case, that's for a conjugated pi system. That's actually centered at 217 nanometers. These are always done in nanometers because if you did it in wave lengths, it would be incredibly long. And so you'd have a lot of problems reading it and dealing with it. So these are always done nanometers. This is the effects of the different structures on your wavelength maxes. Again, notice that you typically just look for your maximum absorption for these things, wavelength max. And typically, more often than not, these are used to monitor concentrations of those things, okay, or absence or presence. So right here, we see some examples. Here we have a double bond. This is an ethene where the double bond's in the middle. This one's at the end, and so it's a little bit higher. Alkanes and cycloalkanes are a little bit lower than 150 nanometers. Anybody have any questions on that table so far? Mm-hmm.
So this is UV absorption before we're looking at.
This is UV
infrared,
vis.
right?
So yes, infrared was before.
Okay.
So that was infrared spectroscopy where we were having absorption in the infrared region. And so this is now absorbing in the UV vis region. We won't cover microwave and we won't cover X-ray. Okay. Or gamma for that matter, yeah. Though gamma ray absorptivity is not really. It kind of just blows up whatever you're looking at. Okay. Anybody have any questions on that so far? All right. What are you noticing about when you have conjugated systems? What do they do? Yeah, so here we have a double bond, one double bond here, one double bond here. This is another single double bonds each, right? And they're not conjugated. And they're all fairly consistent, aren't they? Yeah. If it's in the middle, it's going to be 160 something. If it's at the end, it'll change a bit, 177-ish. But if we have two at the end, that doesn't change each other, right? Still get the same absorptivity. But what if we conjugate them? That's not 278, is it? That one is 216, isn't it? Or 217, excuse me. And so if we conjugate these systems, what you're going to notice is this is going to increase the wavelength max. Okay? And further conjugation actually increases it more. Everybody see it okay? Okay. It also changes depending on if they are cis or trans, just by a little bit. Not by a huge amount. Substituting them also can change it by a little bit, but again, not a huge amount. Them being cyclic actually helps a lot and causes it to go up by a fair amount, but not as much as having another substitution again. So right here we see an example where we have it highly conjugated. Can everybody see you've conjugated all these times throughout here? This is beta carotene, by the way. And this one is going to be 455. And so why did I have you take that UV flashlight when we were doing beta carotene from the spinach? Because it absorbs well in the UV, right? And so I had you go ahead and scan that with the UV flashlight so that you could see these things. Okay? All right, so molecules that contain only sigma bonds do not absorb in the UV or visible regions. Their longest wavelength max, is actually too short. And so you typically see things like sugars, and they're clear, aren't they? They don't absorb in the UV vis very well. You typically see things that are alkanes, for example, don't particularly absorb well in the UV vis. Molecules that contain at least one pi bond tend to have the longest wavelength max. That's greater than 160 nanometers. The value of the longest wavelength max is going to increase depending on the extent of conjugation. Your longest wavelength max tends to be much longer for species that have lone pairs of electrons than a similar species that has no lone pairs of electrons. So for example, things like a nitrogen or an oxygen, right, are going to tend to give you the longest wavelength maxes. Okay. Anything else I need to do there? Okay, so let's rank these species in order of your wavelength max for the longest wavelength absorptions. What would have your longest wavelength max? And then your next one. And then next one. All right, so what will have your longest ones?
V, because it has conjugation in the lone pair.
You got it, you got it. Your conjugated is a big add, right? And then this one also has the lone pair as well, so it's going to be the longest by a lot, right? Okay, so what would be sort of the next ones that would have the long wavelength max? The next longest?
S.
Yeah, S. Oh, and that's because of the lone pairs. Yeah, yeah. That lone pair is going to increase that, isn't it? Then what's going to be the next one? T. Yeah. And then U is going to be so short, it's probably not even going to show up, right? And so it won't even be as typically associated with UV vis. But technically, you could see it on the just below red sort of spectra. Okay? Which is typically called the near infrared. Okay, so the UV vis absorption in colors. The liquid formaldehyde is actually colorless. Its wavelength max is 280 nanometers, and that's why that's colorless. You don't actually see the absorption effects because it's outside of your visible range. Right? Beta carotene, on the other hand, the compound that's going to correspond. Oh, I'm sorry. Short in this case is not near infrared. It's actually above UV. Okay, it's higher energy than you can see. Shorter wavelengths would be high energy, not infrared. It'd be the other way. I went backwards. I had infrared on my mind. Wonder why. Yeah. So beta carotene, this is going to be your compound that's responsible for the colors of carrots, of course. Also, we saw that in spinach. Do you guys know that beta carotene from spinach actually typically is a larger source? You can get more beta carotene from spinach usually. So this wavelength max here is 450 nanometers. And that's why when we look at these, what are you seeing here? Okay, let me ask what you're not seeing. Are you seeing 450 nanometers? No, that's what it absorbs in, right? So that's what it absorbs and you don't see. Okay? So what you're seeing is the absence of 455 nanometers. Right? You're seeing the other colors that are not being absorbed. Primarily the opposite side of the color wheel. Okay? And so this right here is the color wheel. This is actually where your beta carotene absorbs. And so it absorbs blue. The opposite color of that is orange. And so what we see is absence of blue. And then the rest of the spectrum from the sun. And that's orange to our eyes. Okay? Is that making sense so far? Okay. Fantastic. And again, formaldehyde absorbs no visible photons, and so all our wavelengths from the sun pass back through, and we see the same as everything else, right? And it looks clear to us. Okay? Doesn't affect the light coming through in any way that we see. When a compound absorbs particular visible photons, the wavelength is actually removed from our white light, which is a combination of all these colors. Does anybody know what white light actually is? Okay, so white light is our eyes going, there's a lot of light coming in, I can't differentiate all these things. I give up. Okay? If we look at gray, that's actually the same thing, but it's like moderate light coming in, right? Okay? And if we look at like the darker colors like black is going to be where we no longer see enough light, and our eyes are like, I can't see this anymore. I give up. And so those are all actually our eyes going, I give up. Brown is actually where we have like a little bit of red in there. Okay? And so we can kind of differentiate red, but we can't do the rest. Do all species see the same colors, by the way?
No.
Not at all. Yeah, or even the same things. Do you know we look striped to some species?
Strange.
Yeah, because we have UV patterns on us that are striped. So we have stripes, like a zebra. Did you guys know that? Yeah. There's a whole series of weird things like that. Anyways, so what we're looking at whenever we're looking at these different colors is actually absences of the opposite colors. Okay? And that then leaves us the rest of the spectrum coming back out from the sun or the light bulb if we're in a room. All right, so in this case, we absorb blue. Can anybody tell me what the high energy portion of this spectrum is? Ultraviolet. Right there. That's the violet. Ultraviolet would actually be the higher energy than this violet right here. Okay? And then we go around, and red right here, that is the lowest, isn't it? Yep. So that's the lowest energy visible light. And that's actually where the color wheel comes from. It's the highest wrapped around to the lowest. You guys didn't know that, did you? Yep. And this is an artifact of our eyes, how our eyes work. Okay? All right. Does anybody have any questions about that so far? Do you guys know what complementary pairs of colors are? Anybody, who here knows color theory? Has taken art? Good. Fantastic. The rest of you, I'm so ashamed. Okay, so the color wheel is this wheel right here, complementary colors, is where you would have the opposite colors here on the color wheel. These are the things that heavily offset each other because that's how our eyes work. And so, for example, you notice that's typically used for things like Christmas, red and green, sports teams, blue and orange, that sort of stuff, right? So those are the complementary colors. They very heavily offset each other because they're opposites on the color wheel. If you're looking for blending colors, those are actually the ones that are next to it. And so those give you the same sort of tonnage, okay? And can give themes. For example, this is the ocean right there, right? Because they're right offset. Okay. Anyways. Okay, so this is the Beer-Lambert law. Everybody calls it Beer's law because beer is fun. Lambert doesn't sound as fun, does it? Yes. So this right here is absorption. Absorbance equals epsilon, which is the molar absorptivity, or the absorptivity typically is called, times the length, sometimes put as small l, but in some cases put as b, because it depends on if you're working in physics or not. Okay? Some other fields use L for another constant. Okay? Then C, which is the concentration. And so what we see here is this is actually what you kind of already knew. How well does something absorb? Well, if I take like a dye and I add 1 drop to a gallon, is it going to absorb a lot of light?
No.
I add 100 drops? Yeah. It's going to absorb a lot more, right? And so that's concentration, isn't it? Okay. Okay. Can I see through a clear glass of water?
No. Yeah.
Yeah. Yeah. Can I see through the ocean? No. Why is that? Path length, right? My distance I'm trying to see through it is much, much longer. Okay? And so it starts absorbing more and more light as I go. Right? That's why it gets dark when you go further into the ocean, right? If path length didn't matter, that wouldn't matter. Then molar absorptivity. If I'm looking at dye versus clear water, which absorbs better?
Yeah.
Dye. Yeah. That's why I can see the first little part of the ocean, right? Can see in a few inches. If it was dyed heavily, then I wouldn't be able to see it very well, right? Okay. And for example, my absorptivity here is absorbing what color on my shirt?
Everything.
It is absorbing an orange color really well. Okay, that's why it's blue, right? Okay, how about your shirt, Cash? The main shirt part, not the
black or
the black, yeah.
Why? Yeah.
Everything.
Oh, everything.
Yours is absorbing all of visible light fairly well, right? Because it's a pretty deep black, yeah. How about your shirt? Might be a little bit more difficult because it's off color. But in your case, your shirt isn't absorbing super well. But specifically, it's absorbing the opposite of yellow, right? So like a violet color fairly well. Is that making sense for everybody? Okay. Your shirt is absorbing medium. Not as well as his, but across pretty much the whole spectrum, right? Your shirt's not absorbing almost anything. And your shirt is really, really super bright white. And so it's absorbing almost nothing. Yeah. So, yep, there you go. We have the absorptivities. This right here, by the way, is again the amount of light in a specific wavelength or frequency that substance is absorbing. That also is what determines the wavelength max, right? At the wavelength max, your molar absorptivity is going to be the highest. Okay? Okay, so UV vis, again, in quantitative measurements. So this one right here would be the absorbance at 244 nanometers versus time when we'd be looking at this reaction right here. So we put this reaction together. We're trying to figure out, hey, when is our reaction complete? Okay? Okay, so we put these two together. Our reaction starts going, and we have very, very little absorbance, right? Because we're specifically looking at this wavelength max. That's the wavelength we're monitoring. Okay. That wavelength max is because of this conjugation right here, isn't it? Everybody see that okay? So that double bond right here forming is giving us the wavelength max here. Okay. So as we monitor this, what's going to happen to our reactant? It's going to get consumed. It's going to give us product, right? Why is it plateauing?
It can only absorb so much.
And eventually it just gets to be black, right? And we can't see anything else. Okay? And so absorptivity is a logarithmic scale, right? And so it has a logarithmic relationship, and there is a maximum absorption that you can do. And that's going to just slowly approach it over time until you get to essentially a plateau. Okay? Okay, anybody have any questions there? This is actually how you do almost all the kinetics. And when you go into biochemistry, this is actually how most of the kinetics for that stuff is figured out. Okay? So this is one of the primary methods of doing kinetics. Okay, folks. So I will go ahead and do the last two slides, but next time. But we're starting on 17, okay? And we're going pretty far way through 17. So make sure you go ahead and start working on 16. When is the 16 due? Does anyone remember?